Okay, ladies and gentlemen, we're going to do another fun problem here. This is again from UT Homework, courtesy of the UT Quest system. It says that you are standing on the edge of a ravine that is 17 meters wide. You notice a cave on the opposite wall whose ceiling is 6.5 meters below your feet. The cave is 6.7 meters deep and has a vertical back wall. You decide to kick a rock across the ravine and into the cave. At what initial velocity must you give the rock so that the rock barely misses the overhang? The acceleration of gravity is 9.8 meters per second squared. Also, how far down the back wall of the cave will the projectile hit? I think, personally, the hardest part about this problem is figuring out what is going on. So drawing a picture and slowly drawing it and drawing a little piece at a time and trying to work in all the little quirks to it, I think that's the best way to do it. So for me, I started with a ravine. And I know that I'm going to have a cave over here, so I kind of cut a cave out into my little ravine, my little canyon, if you will. And then I know that I'm going to have a rock, and that rock is going to be kicked, and so it doesn't explicitly lay it out. And again, that's another tricky part about this problem. But it's kicked horizontally off the edge of this side of the ravine. And of course, gravity is going to pull it down, and so it's going to follow that parabolic shaped trajectory. And so the overhang into the cave is what you want it to just barely miss, and then it strikes this vertical wall, and you'll want to figure out how far down this wall does it hit. Okay, so looking at this, there's some other parts that are given here, some other sizes and lengths and things, so we should go ahead and indicate those on here. For example, we know that the width of the ravine is 17 meters, so I'm going to put that down, and I'm going to do anything in the X direction in this orange color. I also know that the top of the cave here is 6.5 meters below your feet. So you assume you're standing here, so 6.5 meters below that, that's where the top of the cave stands. And then finally, it's 6.7 meters deep, which means that it's going to cut back this way 6.7 meters. Okay, so now that we have all that, we should be able to start out on our tables. So I'm going to say that in the positive X direction is to the right, and I'll go ahead and just fill out my variables down here. And then for the Y direction, since it's only ever going down, I'm going to go ahead and say down is positive in the Y, and then I'll fill out my variables for this one. Okay, so now we have to try to say what variables are here. We have to identify the values. Some of them are given, some of them are implied. So, starting at the initial position, let's just say that our rock begins at initial position 0, 0, X and Y direction. So I'm going to say my initial position in the X direction is 0, and my initial position in the Y is 0. However, when it reaches this point here that we're interested in, this is our final point in our analysis right now. We have the initial point up top, and the final point is where it skims the overhang. It's gone 17 meters horizontally, so that's my X final. My Y final, I know that it has gone down this way, that's 6.5 meters. And since we've said down is positive, it is a positive 6.5 meters. Okay, and then for the initial final velocity in the X, remember that there's nothing slowing it up or speeding it down horizontally, so therefore my initial and final horizontal velocity are the same, it's constant. But I don't know what it is. That's what it's asking me to find. What initial velocity must you give the rock? But because it is constant, we know that the acceleration is 0. And then, of course, we don't know time yet. But over here, I know that if I've only kicked it horizontally, that it has no initial velocity in the vertical direction, so that's 0. I have no idea what the final velocity in the Y direction is, but I do know that the acceleration due to gravity is what's pulling it down. And so, and again, down is the positive direction, so you just say a positive 9.8 meters per second squared. Again, I don't know time, but I'll be able to find time with one of these and link it to the other, and that's a key to the problem here. Okay, so looking then at these, we want to go ahead and start solving. So to do that, I'm going to go ahead and look at these equations and see what equation I might want to use to do that. It's the Y direction that I'm interested in right now. That's where I have enough information in order to solve. Notice that in the time, or in the X direction, I only have 1, 2, 3 things. And so that's not going to be enough. But over here, I've got 1, 2, 3, 4 different pieces of information. So I'll be able to solve for time in the Y direction. Obviously, time needs to be in the equation, so one of the first two equations will work for us. And The reason I can't pick the first one is because I don't have the final velocity, which would be Vy here. So that means I'm using this middle one right here, the second equation. And so that's going to say y equals y naught plus Vy naught time plus 1/2 ayt squared. Remember that we just are replacing all the x's with y's here. Okay, my y is 6.5 meters, but before I do that, I can cancel this out. Remember that y naught is 0. And then also Vy naught is 0, and so is y naught, so that also goes away. So y is 6.5 meters, so I can fill that out, and then equals 1/2 ayt squared. 1/2 ay, which is 9.8 meters per second squared, multiplied by t squared. Don't forget to say squared on the t here. Okay, so of course half of 9.8 is 4.9 meters per second squared. Divide both sides by 4.9, and you're going to end up getting 1.323 seconds squared, and that equals t squared, because that's what was left over here when you divide it out by 4.9. So obviously take the square root of both sides, and that'll leave you with t is equal to 1.15 seconds. Okay, so I can fill that out in my table for both of these. But again, what I want to know is how fast in the horizontal direction I need to kick it. And now I'm going to have enough information in my horizontal direction in order to solve for that Vx. So again, looking down at the equations, I would have to have Vx in my equation to solve for it, which all three of them have, so really I could use all three of them based off of that alone. But when it comes to the horizontal direction, the first and the third don't always work, because here you'll notice the a term is going to cancel out with acceleration, which leaves you with v equals vx naught. And here the acceleration term cancels out, with which leaves you with Vx equals Vx naught squared. Both are true, but neither are useful. So we go with that second equation. Seems to be our favorite. X equals x naught plus Vx naught time plus 1/2 axt squared. Of course, we can cancel out some stuff here. I know that my acceleration is 0, which means that whole final term is 0, and so is x naught. So now all I have left is x equals my Vx naught, which is just Vx since it's constant, multiplied by time. And so x is 17 meters and time is 1.15 seconds. Divide both sides by 1.15, and you're going to end up getting that Vx is equal to 14.8 meters per second. And that is how fast you must kick the rock in order for it to just barely skim the top of that cliff, or the bottom of that little overhang, if you will. So that's that part of the problem. The next part of the problem said, how far down the back of the wall will the projectile hit? So I can go ahead and just kind of redraw everything here, start from scratch and get some more space. I'm just going to drag the 6.7 down here. And what I'm looking for now is this distance right here, how far down it's going to strike. So delta y is what I am solving for right now. Okay, so then I've got my tables, so I'm just going to kind of drop those down here. And now we can fill them out. Some of the information is the same as before, but some of it is completely different. So we have to be really, really, really careful about that. Okay, we're still going to say that our initial position is right here, and we're going to say our initial conditions or our initial positions are both 0 in my x and the y direction. But it's the final x that is different this time. It's no longer 17 meters. It's going the 17 meters plus the 6.7 meters, which is the depth of the cave. And so that total is going to give me 23.7 meters for my x. The Vx and Vx naught, remember, it's constant, 14.8 meters per second. We solved for that in the last part of the problem, and it's the same even though we have more of the path here because it's constant horizontal velocity. And that's also because the acceleration is still 0. Time is completely different time. We calculated the time it takes to get to the overhang, not the time it takes to get to the back wall of the cave. My initial position in y is 0. My final position in the y is, it goes down 6.5 meters plus another delta y meters. So 6.5 meters plus delta y, that's how far down it goes. Initial velocity in the y is still 0. I don't know the final velocity in the y, but I do know the acceleration due to gravity in the y direction, 9.8 meters per second squared, and again, time I don't yet know. I'll be able to use, though, the y direction with my, or my x direction rather, with my 1, 2, 3, 4 pieces of information in order to solve for time. So now, looking back at my equations, again, when it comes to having 0 acceleration, the first and third equations aren't really going to help. It's the middle one that's going to be that you're going to want. So x equals x naught plus Vx naught t plus 1/2 axt squared. Your ax is 0, so that term cancels. X naught is 0, so that cancels. And it leaves us with x, which is 23.7 meters, is equal to Vx naught, which is 14.8 meters per second, multiplied by time. Of course, I'm solving for time, so divide both sides by 14.8, and I'll have t is 1.6 seconds. Okay, so I'm going to fill that out down here in my table on both sides, and now I'm going to jump over here to the y direction, and now I've got 1, 2, 3, 4 pieces of solid information in order to solve for my delta y. I'm not counting this one in there because it has a variable, an unknown in it. So I'm going to go back and look at my equations again. Well, what equation is going to help me? Thing is, I don't have and don't care to have Vy here. So the equation without Vy is what I'm going to want, which again is our famed equation, the middle one. Y equals y naught plus Vy naught t plus 1/2 AYT squared. So y is, of course, going to be, or y naught is going to be 0, and Vy naught is 0, so those go away. So y is my 6.5 meters plus delta y, and that's equal to 1/2 the acceleration due to gravity multiplied by time squared. Of course, we just calculated the time as 1.6 seconds, so we plug that in here. When you multiply this whole side out, half of 9.8 times 1.6 squared, you get 12.5 meters. So 6.5 meters plus delta y equals 12.5 meters. Obviously subtract 6.5 from both sides, and you're left with delta y equals 6 meters, and that's the final answer. I do want to just give a warning here, a little bit of caution if you're doing this problem on your UT homework. They, of course, want within 1% error. So I did a lot of rounding here. I kept everything to 3 sig figs basically the whole time. So there may be so much rounding that if you were to do it exactly like this, that your answer is not going to be close enough to the exact answer. So be very careful with rounding when you do these problems. All right, that's all.